For decades, we've looked to space telescopes, Hubble, James Webb, Chandra, music, to reveal the universe with clarity that Earth could never offer. But now something unexpected has happened. A telescope still anchored to the ground, still breathing Earth's atmosphere, has delivered images so vast, so detailed, and so shockingly deep that astronomers around the world stopped what they were doing. Because for the first time, the Vera C, Rubin Observatory has opened its eyes. Music, and what it saw on its first night, isn't just beautiful, it's unsettling. It's a music glimpse into a sky so crowded, so dynamic, so alive with activity. Music that it threatens to rewrite how we map the universe. A camera the size of a small car, capturing 3.2 billion pixels at once. A single exposure, music wide enough to hold 40 moons. A data set that will grow so massive it will take lifetimes to interpret. And yet the very music, first images already contain secrets. Merging galaxies, newborn, music stars, tens of thousands of ancient clusters, and more asteroids in 10 hours than music the rest of humanity found in weeks. This is the moment astronomers have waited for. A machine powerful enough to watch the sky change, to catch cosmic events in the instant they happen, to reveal structures we didn't even know existed. Tonight we're diving into what the Vera Rubin telescope has music just seen and why its first images have shaken the scientific world. Long before the first images were released, the Rubin Observatory was already a legend waiting to be born. Perched atop Cerro Pachón in Chile, one of the driest, music-clearest, darkest places on Earth, it was designed not just to take pictures, music, but to survey the universe in a way no other observatory ever has. Music, its heart, is the Simone Survey telescope, a three-mirror design unlike typical two-mirror systems, giving a sharpness and field of view unmatched by telescopes, music of its size. The primary mirror alone spans 8.4 m. Music, but what truly sets Rubin apart is the fusion of its optics with the largest digital music camera ever built. This camera weighs nearly 3 tons, stretches 3 m long, and captures ultraviolet, visible, and near-infrared light with stunning precision. But where Rubin begins to defy expectations is in its scale. One image covers music 10 square degrees, an area equivalent to 45 full moons. In a single music snapshot, Rubin sees what would take Hubble thousands of images to assemble. And as it completes music, it scans every 3 days. It doesn't just produce static portraits. It builds a time-lapse movie of the universe, exposing the flickers, pulses, collisions, and transformations happening all around us. This is not a music telescope built to look at one object. It is built to look at everything all at once. When Rubin captured its first music images in June 2025, astronomers expected something impressive. But they were not music prepared for what the observatory actually delivered. After just over 10 hours of test observations, music, Rubin produced a mosaic that the scientific community quickly nicknamed the cosmic music treasure chest, a breathtaking 25 square degree portrait of the southern Virgo cluster, the closest large music galaxy cluster to the Milky Way. This image, stitched together from 1,185 exposures, music contains millions of stars and galaxies. Spiral galaxies stretch their arms lazily across space. Merging galaxies twist together like cosmic smoke. Filaments connect, music, distant clusters in web-like structures. In the background, barely visible unless you zoom in, lies a sea of faint reddish galaxies, each one a possible host to billions of planets. And this overwhelming richness represents music, 0.05% of what Rubin will detect. The observatory is set to reveal 20 billion galaxies, and this first mosaic is just music, the preview. The trailer for a decade-long film, The Universe, is about to broadcast through Rubin's lenses. As astronomers explored the mosaic, they found not just beauty, but unfiltered cosmic evolution. Structures forming, interacting, fading, expanding, captured in detail so immense that it reshapes our understanding. music of what a first image can be. If the first mosaic demonstrated Rubin's power, its next music release proves something even more astonishing, that a ground-based telescope could rival space music observatories in depth and scale. The Rubin team unveiled a wide-field mosaic music of the Lagoon Nebula, a star-forming region about 5,200 light-years away. Normally, when we see the Lagoon Nebula, it's through narrow, zoomed-in images from telescopes, music like Hubble. But Rubin showed us something else entirely. A panorama where the nebula, despite music spanning 55 light-years, occupies only a fraction of the frame. Surrounding it are countless music points of light, open clusters like Messier 21, the glowing Trifid, music, nebula, Bok globule 14, and the densely packed globular cluster NGC 6544. In a single image, Rubin captured structures, music, that exist at wildly different distances and scales, from newborn stars in the nebula's core to ancient globular music clusters thousands of light-years further away. This is the consequence music of Rubin's staggering field of view. Hubble sees 1% of the moon's surface in a single image. Rubin sees music 40 moons at once. And yet, even with this immense view, its details remain sharp, intricate, layered. For the music, first time we see the lagoon not as an isolated object, but as a connected piece of a much larger cosmic music landscape, a neighborhood filled with birth, death, chaos, and motion. Rubin wasn't built music just to create pretty pictures. It was designed to revolutionize astronomy. And even in these early tests, it's already doing exactly that. In just music, 10 hours the observatory identified 2,140 new asteroids, including 7 near-Earth asteroids. To put that into perspective, music, the world's combined observatories typically detect around 20,000 asteroids a year. Rubin is poised to discover millions in its first few years alone. It may become the single greatest tool humanity has for detecting and tracking music potential impact threats long before they come near our planet. And this is only one of its 4 major missions. Rubin will also search for dark matter and dark energy by mapping music, how galaxies cluster and move across billions of light years. It will monitor transient events, music, supernovae, gamma-ray bursts, star quakes, catching them in real time thanks to its music rapid scanning cycles. It will trace ancient RR Lyrae stars, potentially identifying 100,000 of them to map the outer edges of the Milky Way like never before. And behind music, all of this lies the true behemoth. 500 petabytes of data expected by the end of the survey. Trillions of measurements, billions of celestial objects, a decade-long time-lapse of the universe that will take generations to fully unpack. Rubin is not just a telescope. It is music, a cosmic machine built to rewrite humanity's astronomical playbook. To understand why the Vera Rubin Observatory's first images shocked astronomers, music, so deeply you have to consider the challenge of taking crystal-clear pictures from music, the surface of a planet wrapped in turbulent air. Ground-based telescopes live in a world of atmospheric blur, music, temperature shifts, humidity, dust, and even faint layers of distortion invisible to the naked eye. It's why observatories like Hubble and James Webb were launched, music, into space in the first place, to escape Earth's atmospheric cage. And yet, music, Rubin breaks this rule. Built on the cliffs of Cerro Pachon in the Atacama Desert. Music, it sits in one of the driest, darkest, most stable air columns anywhere on Earth. This is a place where rainfall is almost non-existent. Music, where clouds are rare, where light pollution is essentially zero. In fact, the Atacama hosts some of the world's most important telescopes for exactly music. This reason. Rubin takes advantage of this location in a way few ground-based observatories ever have. Combined with its 3-mirror optical system, music, its massive camera, and its automated nightly scanning, Rubin manages to bypass many of the atmospheric constraints that limit most observatories. The result is images so crisp and so wide that they rival, sometimes surpass, those taken from orbit. For a ground telescope to achieve, this is not just surprising. It is revolutionary, and it signals a new era where Earth-based and space-based observatories might finally stand side by side, not as rivals, but as partners unlocking the same cosmic mysteries. One of the most staggering achievements of the Rubin project isn't the telescope itself, but the invisible digital infrastructure required to make sense of what it captures. Rubin is expected to collect 20 terabytes of data per night, an amount so massive that traditional observatory networks would collapse under the load. To overcome this, engineers built a dedicated 100 gigabit per second fiber connection that beams the data directly from Chile to a data center in the United States. From there, the information enters a processing pipeline that must act in real time, calibrating images, aligning exposures, correcting distortions, identifying moving objects, labeling transient events, and integrating new data into a constantly growing map of the sky. All of this happens before scientists even begin their analysis. What Rubin is creating is not a collection of images, but a dynamic digital universe, one that updates itself every 3 days. Imagine replacing static star charts with a living, breathing model that responds to changes faster than astronomers can even react. A supernova flares into existence. Rubin catches it. An interstellar object streaks through our system. Rubin sees it. A star pulses irregularly. Rubin records it. The observatory doesn't just observe. It learns, tracks, and adapts. It is, in a sense, the first telescope designed for the era of big data. A machine built to convert the night sky into an ever-expanding cosmic database. While Rubin's wide-field imaging is breathtaking, its true power lies in its ability to capture time. Every 3 nights, the telescope completes an entire scan of the southern sky, allowing astronomers to watch celestial events unfold with unprecedented immediacy. Supernovae that once went unnoticed until they were already fading will now be recorded in the instant they ignite. Gamma ray bursts, tidal disruption, events, variable stars, shock waves through nebulae. Rubin will catch them all. This capability transforms astronomical research from passive observation into active monitoring. Rubin becomes the universe's alarm system, detecting changes, and broadcasting them instantly to scientists around the world. Before Rubin, these brief and unpredictable events were easy to miss, appearing in narrow telescope fields or between scheduled observations. But Rubin's constant monitoring changes everything. It builds a cosmic heartbeat, a rhythm of detection that captures the universe, not as a static snapshot, but as a living, dynamic organism. Think of it as the first telescope that watches the sky the way security cameras watch a city, taking in everything all at once, waiting for the unexpected. The scientific implications are enormous. Transients reveal hidden physics, stellar deaths, collisions, births, and the violent processes shaping galaxies. Rubin will catch thousands of them, many never seen before. And each one has the potential to rewrite a chapter of astrophysics. Beyond galaxies and transients. Rubin's first observations of RR Lyrae stars hint at another transformative discovery, the ability to map the Milky Way's structure in unprecedented detail. RR Lyrae stars are ancient pulsating objects used as standard candles. They vary in brightness in predictable cycles, allowing astronomers to calculate their distances with remarkable precision. Rubin has already identified 46 RR Lyrae in its test images alone, and scientists expect that number to grow to 100,000 over the full survey. These stars often lie far from the Milky Way's core, floating in the outskirts of the galactic halo, or even stretching into intergalactic space. Tracking them creates a skeletal map of our galaxy, revealing faint tidal, music streams from past collisions, hidden dwarf galaxies, and the true three-dimensional shape of the Milky Way's outer reaches. For decades, astronomers have struggled to map these distant regions because the stars are too faint and too sparse. But Rubin's massive field, of view, deep imaging, and repeated scanning turn the impossible into the routine. The observatory becomes not just a camera, but a cartographer, charting the ancient architecture of our galaxy and uncovering remnants, of cosmic history written in the stars themselves. By the time Rubin completes its 10-year mission, our understanding of where we live in the universe may look nothing like it does today. Most telescopes rely on standard CCD detectors, but the Rubin Observatory uses something far more ambitious, a 3.2 billion pixel camera, the largest astronomical camera ever built. This is not a simple imaging device. It is a precision-engineered machine designed to capture wavelengths from ultraviolet to near-infrared with incredible sensitivity. The camera itself is nearly 3 m long and houses 189 individual sensors, each carefully calibrated to ensure seamless stitching across monumental exposures. But the secret to its unprecedented clarity lies in its trio of fused silica lenses, one of which holds the title of the largest lens ever made for astronomy. These optical elements work together to eliminate distortion across Rubin's enormous field of view, ensuring that a star at the edge of the image is just as sharp as one at the center. Its robotic arm system swaps filters at remarkable speed, allowing the observatory to transition between ultraviolet, visible, and infrared observations effortlessly. The result is not a photograph in the traditional sense. It is a multi-dimensional data tapestry. Every exposure contains layers of information invisible to the human eye: chemical signatures, thermal clues, spatial distortions, and motion trails. Rubin doesn't just take pictures. It extracts the universe's hidden structure frame by frame. While the Hubble Space Telescope captures images at an extraordinary level of detail, its field of view is tiny, equivalent to just 1% of the moon's surface. It is engineered to zoom into cosmic objects like galaxies, nebulae, or star clusters, revealing narrow regions with microscopic precision. Rubin, however, was never designed for close-ups. With its 8.4 m primary mirror, vast camera, and sweeping optical system, its purpose is scale. One Rubin image can capture a sky area equal to 40 full moons. That means Rubin exposes cosmic context, the relationships between galaxies, the filaments connecting clusters, the sprawling architecture of nebulae. When you compare Rubin's wide-field lagoon nebula mosaic to Hubble's tight portrait, the difference is almost shocking. Hubble sees a window. Rubin sees the entire landscape around it. Hubble allows us to study the anatomy of a star-forming region. Rubin allows us to understand how that region fits into the galaxy's ecosystem. In this sense, the two observatories are complementary. One is a microscope. The other is a panoramic drone soaring above the cosmic terrain. And Rubin's first light images prove that the universe looks very different when you finally step back far enough to see the bigger picture. Skyviewer, that app isn't just an educational tool. It's an invitation for anyone, anywhere, to explore data that would once have been accessible only to professional astronomers with high-performance computing systems. Because Rubin's images are so enormous, some built from over 1,000 exposures. Zooming through them feels like moving across a living map of the universe. A user, can dive from wide cosmic landscapes into clusters, down into individual stars, and then out into galaxies that appear as faint specks only when viewed at full resolution. The platform, is the beginning of something revolutionary, a world in which citizen scientists and enthusiasts participate directly in discovery. Hidden supernovae, rare stellar pulses, faint comets, even music, interstellar visitors could be spotted first by someone scrolling casually through Rubin's mosaics. Astronomy is becoming democratized through Rubin's openness. And with half a petabyte of data coming each year, the scientific world will need all the eyes it can get. Astronomers estimate that one interstellar object passes, music, through our solar system every year. But until recently, we lacked the capability to detect most of them. Objects like Oumuamua and 2I/Borisov were found almost by accident, music slipping past our instruments with only days or weeks of visibility. Rubin changes music that its wide field of view and rapid 3-day scanning cycle mean it can pick up faint, fast-moving objects long before music they get close to the sun, precisely the window of time when they're easiest to study. In its very first test run, Rubin identified over 2,000 new asteroids, including several near-Earth ones, demonstrating that it is already capable of spotting unusual trajectories. For interstellar science, this is transformative. Rubin may detect dozens music of interstellar visitors during its decade-long survey, giving scientists the music chance to analyze their composition, structure, and motion in real time. These objects are snapshots of other solar systems, material forged around alien stars, music carrying chemical histories we've never encountered before. Rubin could therefore become humanity's first reliable gateway to studying the raw debris of distant worlds. Music, and with enough detections, researchers may even begin to answer questions that Oumuamua raised but never resolved, including whether some of these visitors are entirely natural or not. In the end, what the Vera Rubin Observatory has revealed in its very first images is not simply a new chapter in astronomy. It is the beginning of an entirely new language for understanding the universe. For decades, music, our vision of the cosmos, has been shaped by narrow windows, tiny fields of view, single snapshots, isolated regions of space. Music studied one at a time. But Rubin breaks that paradigm completely. Its first images already show us that the sky is music, not a quiet dome sprinkled with stars. It is a dynamic tapestry in constant motion, overflowing music with structure, evolution, and phenomena we've barely begun to classify. A single mosaic captures millions of galaxies at once. A 10-hour music scan exposes thousands of asteroids we didn't even know existed. A wide-field view of a nebula reveals not just a star-forming region, but the cosmic neighborhood surrounding it, a cradle of gas, clusters, filaments, and music, ancient stars stitched together across unimaginable distances. Rubin doesn't just collect data. It compresses music, the living universe, into a format we've never seen before. A time-lapse of existence itself, updating every 3 days, building a cosmic memory that will grow music to 500 petabytes by the end of its mission. It is a machine designed not just to observe music, but to anticipate, capturing events the moment they happen. Supernovae erupting, music gamma ray bursts detonating, celestial visitors streaking in from other star systems. For the first time, we are watching the sky the way the universe intended, as something alive, dynamic, unpredictable, and endlessly evolving. And Rubin is only at the beginning of its journey. Its wide-field precision is already rewriting the rules of astrophysics. Its scanning cadence is redefining how we detect interstellar objects. Its RR Lyrae detections are mapping the skeleton of the Milky Way. Its unprecedented images are bridging the gap between professional astronomers and the public, allowing anyone to zoom through the cosmos with tools once reserved for experts. Rubin is not just a telescope. It is a shift, music, in perspective, a signal that the era of static astronomy is over and the era of cinematic astronomy, music, has begun. And when we consider what this means for the next decade, the discoveries, music, the surprises, the cosmic alarms that Rubin will set off, we realize something profound. This telescope will change what music humanity knows about the universe more in 10 years than we learned in the last 50. Everything is about music to accelerate. Everything is about to expand. The universe has never been more ready to reveal itself. Music, and we've never been more prepared to see it. If you want to follow every discovery Rubin makes, every asteroid, every supernova, every interstellar visitor, every cosmic shockwave, make sure to subscribe, turn on notifications, and stay with us because the next image, music, Rubin sends might not just change astronomy, it might change the world. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.